Self-consistency is a lightweight, unsupervised technique for improving large language model performance by sampling diverse responses and grouping them to find the most consistent answer. In our work, we explore how to apply self-consistency to the visual domain. More specifically, we focus on the task of motion trajectory generation for motion graphics animations. In these animations, people often describe object trajectories in terms of geometric shapes, such as parabolas, figure eights, sine and cosine waves, and spirals. Here, we can ask for a spiral path with a prompt like this, and get a variety of trajectories from an LLM. Now, to apply self-consistency to find the correct trajectories, the key question is how we can know which trajectories are consistent to each other. For these geometric shapes, one way is to use geometric transformations, such as rigid, similarity, and affine warps. Here, we group the trajectories with a similarity warp and obtain clusters with various sizes. And the largest cluster here represents the most consistent answer. In this case, the largest cluster does give us the correct collection of trajectories that match with the prompt. Formally, this group of trajectories form a shape family where any member of the family can map to any other members under a particular warp. Now, with this shape family recovered, the task of generation becomes simply returning any member as the result. We can also use this family to perform verification. Given a new trajectory, verification is equivalent to checking if that trajectory belongs to the family under the geometric transformation. So, the key to recover the correct shape family is in the geometric warp. But what if we don't know which warp to use? To address this, we begin by first considering a hierarchy of 6 common geometric transformations based on their Lie group relations. Moving from the bottom up, this hierarchy progressively allows for more degrees of freedom. With this hierarchy, we apply every warp to cluster the trajectories and propose 2 decision criteria to choose a warp by looking at the clusters in a bottom-up manner and a top-down manner. To evaluate our extension of self-consistency, we develop a benchmark of prompts describing 35 different base geometric shapes. We generate each prompt with a template-based approach, and manually pair each prompt with a ground truth shape family for a total of 224 prompts. When evaluating our approach on this benchmark, we see an increase in accuracy against direct LLM sampling without self-consistency, and an increase in precision and overall F1 score for verification when compared to VLM baselines.